And all of this business here simply converts the reciprocating motion of the piston, which is working in the cylinder, to the rotary motion required for the crankshaft. I can lift the cover up. And you can see the crank, the connecting rod, and the shaft itself. Now, we have our generator mounted on the side of the engine. There was no fixed rule as to how many cylinders, where the generator was mounted. This is a small engine. I should say this is 75 kW. Among the biggest steam engines ever built were the ones from the Transit Authority 59th Street Powerhouse. One of them would have taken half of this room and another story. They had a capability of 12,000 horsepower under overload. This is 100, so you can imagine you're blowing this up 120 times. This, of course, is your generator proper. This holds your field coils. Your field coils give you the magnetic field through which the armature is turning. So actually, the engine is turning the armature. When you say the engine is driving a generator, that's not absolutely correct in the sense that the whole thing is the generator. All the engine is really turning is the armature. That's nitpicking, however. The armature has copper bars in it, as you've undoubtedly gone into. We have a very intense magnetic field between those black coils that you see inside the frame. These are actually electromagnets. A small amount of the current that you generate is fed back into them to create the magnetic field. As the armature moves the copper bars through that field, the current is generated. Now you have the problem of having a generated current in a moving object which does you no good. You need it over here. That's where the commutator comes in. The commutator is simply, in our case, 212 copper bars, each of which is connected to one end of an armature coil. So, we have current in our commutator. How do we get it off? Brushes. Carbon brushes, which are riding on the commutator. The brush position, years ago, could be controlled. In other words, you've got a hand wheel here. The whole brush assembly could be moved slightly because the technology was not absolutely perfect. You might have 2 or 3 different engines, have the brushes in exactly the same spot. One might run good and 2 might have excess sparking on the commutator. So by means of this hand wheel, you can actually rotate the whole brush assembly slightly to find your point of best commutation. To solve that problem, they went into interpoles, which is what you'll see on the turbine if you're looking at it that way, which is simply a smaller coil. The problem is, when you're moving a copper armature bar through a magnetic field, you're creating an electrical current in that bar. But what happens when you pass electricity through a conductor? You're creating another magnetic field, admittedly a very weak one. But the armature, the spinning armature's magnetic field is strong enough to slightly distort the magnetic field of the main pole. Again, this is why you can move the brushes to compensate for any distortion of the main field. When they went into the next stage of development, they put auxiliary fields in between the main field to strengthen the main field and to minimize that distortion. So once you got beyond the turbine, that's a transitional piece because that has both the ability to move the brushes and the interpoles. But when you got beyond that, you find that the brush positions are fixed because the designer already knows what's ideal.